already, please make sure to do so. Also, link to buy me coffee and channel memberships in the description as well if you were interested in that. But yeah, so glad to have you back. As you can see, today's video will be the second part of the periodic table of elements. If you haven't seen part one, you can go and check that out. It doesn't really matter, you don't really need to watch them in order, it's like whatever you want. But yeah, I will be starting off from where I left off. So I stopped at 59, so we're going to be starting at 60 all the way to 118, since there are 118 elements on the periodic table. So I just kind of divided the total amount in two, just so it would be even last time, because I knew I wouldn't get through it in one video. So we're doing 3 facts for every single element, because that is what I did last time. Last video was uploaded a while ago. Apologies, I never ended up filming it before I went away for the marathon, and then I've been filming other things just because I already had the setup for the other video. It just takes a few minutes to like set up the camera in the correct position, all of that. So I was like, I might as well film 2 of the other way, but I've been more time today, etc. So I decided I should get back to doing this one. Why not? So I hope you guys are doing well. I guess I will get straight into it. Everything is going well with me. I'm starting my 10k plan today already, basically, but I just start with strength training. If you're a runner, don't forget your strength training. It is important. It helps prevent injury, helps you get stronger, all of that stuff. And yeah, I'm excited for the new training block, and that's not going to be super intense like a marathon, but then again, will still be, adequately challenging, etc. with intervals. So yeah, I thought I'd just get right into it. Why not? So the first one we are doing is 60, so we're continuing in these blue section for now, because the elements go like, and then you go down here, and then you go up here, and then you go back down here, and then you go back up here. A little confusing, but yeah. So the 60th element is neodymium, Nd. As per usual, I'm probably butchering the pronunciation of all of these, but ayo. So it's essential for creating strong permanent magnets used in electric motors, wind turbines, and headphones. It gives a purple color to glass and ceramics. Neodymium glass is used in laser technology. Neodymium magnets, ND-FeB, are among the strongest known types of permanent magnets. Oh yes, and if I didn't say already, the symbol is Nd. So next up, 61, promethium. Sorry for background noise, things are just going on in the background. Some people tend to slam doors as they're cooking, drawers, etc. This is just the best time for me to film it, so sorry if you hear any of that. So PM, a rare radioactive metal that does not occur naturally in significant amounts on Earth, used in luminous paint, atomic batteries, and for better radiation in thickness gouges. Discovered in the byproduct of uranium fission in nuclear reactors, can be found in trace amounts in uranium ores. So samarium, SM. Samarium, used in samarium cobalt magnets, which are highly resistant to demagnetization and work well at high temperatures. Employed in neutron capture to control nuclear reactors due to its ability to absorb neutrons. Found in alloys and materials that enhance the stability of glass and ceramics. So europium, EU, so 63. for producing the red colour in TV and computer screens and in fluorescent lamps, has applications in anti-counterfeiting measures such as euro banknotes, highly reactive, more so than most of the lanthanides, and can ignite in air. And yes, we are in the lanthanides category. Lanthanides, so hard to pronounce some of these things. So gadolinium GD. Oh wait, I think I was meant to be moving the focus as I was doing this. Oh well, I don't think it makes too much of a difference, but yeah. Used in MRI contrast agents due to its strong magnetic properties. Plays a role in shielding in nuclear reactors as it can absorb neutrons. Gadolinium compounds are utilized in phosphors for color TV tubes and LEDs. So, terbium TB. Used in green phosphors for TV and computer screens as well as fluorescent lamps. Found in alloys to improve the magnetorestrictive properties such as terphenol D. Terbium doped materials are used in solid state devices and fuel cells. Dysprosium DY. Important for making high strength magnets that retain their magnetic properties at high temperatures. Used in nuclear reactor control rods due to its high neutron absorption capability. Dysprosium-based alloys are employed in laser and data storage applications. So, holmium. Just have the feeling that I'm saying everything wrong. So the symbol is HO, has the highest magnetic strength of any element used in high strength magnetic fields. Found in certain solid state lasers that emit infrared light. Holmium oxide is used as a yellow or red colorant in glass and cubic zirconia. So, erbium. Used as a dopant in fiber optic cables to amplify signals in telecommunications. Gives a pink hue to glass and ceramics, often used in decorative items and glazes. Employed in certain laser medical applications such as dermatology and dentistry. And the symbol is EOR if I didn't say. So, thulium. TM, one of the rarest lanthanides used in portable X-ray machines as a radiation source. Thulium doped lasers are used in surgical procedures and medical imaging. Has limited applications due to its high cost and rarity. So, ytterbium. This YB, so this is spelled a bit like you wouldn't think to say like this YTT or ytterbium, like you'd expect like a vowel after a Y, usually, right? It's like in some people find perhaps Irish names and a bit weird because there's like sometimes so many consonants in a row without like a vowel. So like say sieve, it's even at first I thought it was kind of weird to spell. It's like SADHBH, like 4 consonants in a row like that. So sometimes we just like put them all together and people find it hard to pronounce if you don't know how to pronounce them. So used in atomic clocks and as a dopant in certain types of lasers. Ytterbium compounds are employed in stress gauges and in some solid-state devices found in certain alloys that improve the mechanical properties of stainless steel. So yeah, if you notice that some are kind of repeating themselves a little, it's because, of course, these elements are gonna have like some common uses, like some elements are used in similar purposes, or maybe they have slightly different, uses in the same purpose. So like we already heard about used in like gouges, etc. So 71, lutetium. So the densest and highest atomic number of the lanthanides used in PET scan detectors, and it's Lu, often used as a catalyst in petroleum refining and in organic synthesis, found in certain specialty glass and ceramic products due to its stability and hardness. Okay, so that's all for those. Now we're gonna move on up here again, which we did in the last video. So wait, am I in the right place? Yes. Back here. So to transition metals. So 72 is hafnium, HF. Okay. So used in control rods for nuclear reactors due to its high neutron absorption capacity. Often found in zirconium minerals and is difficult to separate from zirconium due to their similar properties. Used in the production of superalloys for jet engines and spacecraft components. I often forget how many elements there actually are and like how useful they are in our day-to-day lives and for medical purposes and all of this. So it's nice to appreciate all the elements. So tantalum, Ta. Highly resistant to corrosion and is used in the manufacturing of surgical instruments and implants. Commonly used in capacitors and high power resistors in electronic devices like smartphones and computers. Found in the mineral coltan, which is mined in various parts of the world, including Africa. So tungsten, W. Tungsten, the W is the symbol. So it has the highest melting point of any metal, 3,422 degrees Celsius or 6,192 degrees Fahrenheit, and is used in light bulb filaments and cutting tools. Known for its high density, comparable to gold, and used in military applications for projectiles. Tungsten carbide is widely used in industrial machinery and drilling tools for its durability. Okay, so rhenium or E. And one of the rarest elements in Earth's crust, and has a high melting point, third highest after tungsten and carbon, used in jet engine components and superalloys due to its high temperature stability. Rhenium catalysts are essential in the production of high octane gasoline. So osmium, OS. in fountain pen nibs, electrical contacts, and other applications where durability and hardness are required. Osmium tetroxide is used in staining biological samples for electron microscopy, although it is highly toxic. So, iridium ore, extremely corrosion resistant and often used in spark plugs, crucibles, and electrical contacts. Found in meteorites and is used as a marker for the Kt boundary, linked to the extinction of the dinosaurs. One of the densest elements used in high-end pens and deep sea equipment. So platinum. A precious metal known for its use in jewelry, catalytic converters, and laboratory equipment, widely used as a catalyst in chemical reactions, including in the production of hydrogen fuel cells, resistant to tarnish and corrosion, making it highly durable. So now is one that we should all know: gold, or AU. Highly valued for its use in jewelry, investment as a standard for currency, conducts electricity well, and is used in electronics and computer circuits. Non-reactive, so it doesn't tarnish or corrode, making it useful in many applications. So another well-known one, mercury, Hg. The only metal that is liquid at room temperature, historically used in thermometers and barometers, used in fluorescent lighting and dental amalgams, although its toxicity has reduced its use. Exposure to mercury vapor can be harmful and leading to neurological damage. So, thallium 81 or TL. So, yeah. Thallium, extremely toxic and historically used in rat poison and insecticides. Its use is now restricted. Thallium sulfate is used in some medical procedures such as stress tests to evaluate heart health, found in trace amounts in minerals and extracted from lead and zinc ores. So next up is lead, or Pb. Known for its historical use in pipes, paints, and gasoline, now restricted due to toxicity, has applications in batteries, especially in lead acid batteries for vehicles. Lead shielding is used to block harmful radiation in medical and industrial settings. Bismuth, or Bi, has the lowest toxicity of any heavy metal and is often used in medical and cosmetic products, used in certain fire detection systems and sprinkler heads due to its low melting point. Bismuth compounds are found in antacids and stomach remedies such as bismuth subsalicylate Pepto-Bismol. So, polonium PO. Highly radioactive element discovered by Marie Curie and named after her homeland, Poland. Used as a heat source in space probes and as an anti-static device in some industrial applications. Extremely toxic due to its intense radioactivity, making it dangerous even in small amounts. Astatine AT. The rarest naturally occurring element on Earth, only trace amounts present. Highly radioactive and has very short half-life, so has limited practical uses. May be used in targeted alpha particle therapy for certain types of cancer. So, radon, or N. A radioactive noble gas that forms from the decay of uranium and can accumulate in homes, posing health risks. Known for being a significant cause of lung cancer after cigarette smoking. Used in some medical treatments, particularly in radiotherapy for cancer. So now we're moving on to the next line. So a little at the edge of the screen here, but francium F4. Okay, the second rarest naturally occurring element, highly radioactive and decays quickly. Exists only in trace amounts in uranium and thorium ores with no significant commercial applications. So unstable that it has never been observed in macroscopic amounts. So next to that one is radium, or A. Discovered by Marie and Pierre Curie and historically used in luminous paints for watch dials, instrument panels, and clocks. Highly radioactive and glows faintly due to its radioactivity. Exposure can lead to serious health effects, including radiation sickness and cancer. Used in early medical treatments for cancer, though it has largely been replaced by safer radioisotopes. And this was something to do with, like, I feel like in history, and there was also a Netflix show on this. I can't remember, like, I didn't watch it, but it looked interesting. This woman that worked in these factories to, like, on watches or watch dials or something intricate, but the radium in the watches or something were actually making them have cancer. And then someone discovered this and like to storm out or something, like the people were kind of covering it up or something because they wanted them to still work on this. They didn't really care about their health or anything. They weren't paid well at all as well. So, it's not over here. The next one is actually down here. So now we're moving on to actinides. So, actinium. AC, the first element of the actinide series, discovered in 1899 and named after the Greek word actinos, meaning ray or beam. Radioactive and used in radiation therapy for cancer as a neutron source. Rarely found in nature, usually occurring in uranium and thorium ores. So, thorium TH. Okay, so abundant and more common than uranium, considered as a potential fuel for nuclear reactors, used in gas mantles for camping, lanterns, and portable lighting due to its high temperature incandescence. Its decay contributes to the eternal heat of the earth and plays a role in geothermal energy. So, protactinium, Pa. Rare and highly radioactive, found in uranium ores and often extracted as a byproduct of uranium processing. Discovered by German chemist Otto Hahn and initially called protoactinium for its role as a precursor to actinium, used mainly for scientific research due to its rarity and radioactivity. Uranium U. So, best known for its use as fuel in nuclear reactors and the production of nuclear weapons. Occurs naturally and is found in a variety of minerals such as uranite and pitch blende, used in the past for coloring glass and ceramics, giving them a yellow to green hue. So, Neptunium NP. The first trans-uranium element discovered and named after the planet Neptune, produced in nuclear reactors as a byproduct of plutonium production and used in neutron detection instruments. Highly radioactive and has been studied for potential use as fuel in fast neutron reactors. So, Pt.2. Best known for its use in nuclear weapons and as a fuel source in nuclear power plants and space exploration, for example in radioisotope thermoelectric generators. Discovered during the Manhattan Project and named after the dwarf planet Pluto. Highly toxic and radioactive, with its most common isotope being plutonium-239, which is used in nuclear warheads. Mercurium AM. So, found in household smoke detectors as a ionization source due to its alpha radiation properties. Discovered in 1944 as part of research for the Manhattan Project and named after the Americas. Used in industrial gauges to measure thickness and density of materials. Curium CM. Named after Marie and Pierre Curie in recognition of their contribution to the study of radioactivity. Used as a power source in spacecraft and satellites as it decays, releases a significant amount of heat. Not found naturally and is produced in nuclear reactors by bombarding plutonium with neutrons. Berkelium BK. First synthesized at the University of California, Berkeley, and named after the city. Used in research and has no significant commercial applications due to its scarcity and radioactivity. Plays a role in the synthesis of heavier elements such as californium CF. Named after the state of California, where it was first synthesized at the Berkeley lab in 1950. Used in neutron sources for detecting gold and silver in mining, and in neutron activation analysis for identifying elements in samples. Highly radioactive and must be handled with great care due to its strong emission of neutrons. Einsteinium ES. Named after Albert Einstein and discovered in the debris of the first hydrogen bomb explosion in 1952. Used for scientific research and has no significant commercial uses because of its rarity and radioactivity. Difficult to produce in substantial amounts, making it primarily a research curiosity. Fermium FM. Named after physicist Enrico Fermi, a pioneer in nuclear physics. Discovered in the fallout from the first hydrogen bomb test, similar to Einsteinium. No practical applications outside of basic scientific research due to extreme radioactivity and limited availability. So, Mendelvium MT. Named after introduced. Nobelium NO. In honor of Alfred Nobel, the inventor of dynamite and founder of the Nobel Prizes. First reported synthesis was in 1957 at the Nobel Institute of Physics in Sweden, though confirmed later by other laboratories. Highly radioactive with no practical applications outside of research due to its short half-life. Lawrencium L-Or. Named after Ernest O. Lawrence, who invented the cyclotron, first synthesized in 1961 at the Lawrence Berkeley National Laboratory. Its chemistry is still being studied, but has no significant uses beyond research. So now we're moving back up here, and this is the final line. So, Rutherfordium, or F. Named after Ernest Rutherford, known for his pioneering work in nuclear physics, first discovered in the 1960s by teams in both Russia and California. Its chemical properties are similar to those of hafnium and other group 4 elements studied primarily in labs. So, dubnium DB. Named after Dubna, Russia, where it was first synthesized, discovered in the 1960s by joint American and Russian teams, leading to disputes over its name until agreed upon in the 1990s. It has no practical uses and is studied only for research purposes due to its short half-life. So that seems to be a recurring theme with some of these elements. So Seaborgium Sg. Named after Glenn T. Seaborg, who contributed to the discovery of many transuranium elements. First synthesized in 1974 by a team at the Lawrence Berkeley Laboratory, exists only in trace amounts with no practical applications outside of scientific research. Bohrium BH. Named in honor of Niels Bohr, a major contributor to the understanding of atomic structure, first created in 1981 by a team in Germany at the GSI Helmholtz Center for Heavy Ion Research. Highly unstable and studied solely in research laboratories. Okay, Hassium HS. Named after the German state of Hesse, or Hesse, I'm not sure, where it was first synthesized in 1984 at the GSI, predicted to behave similarly to osmium with properties typical of group 8 elements, has no commercial applications, and is studied to understand the behavior of super heavy elements. So now we're moving on to some unknown properties. So, Mednerium MT. Named in honor of physicist Liza Medtner, who played a key role in the discovery of nuclear fission. First synthesized in 1982 by a team led by Peter Armbruster and Gottfried Münzenberg in Germany, exists only momentarily before decaying and is of interest purely for nuclear research. So, Darmstadtium DS. Named after the city of Darmstadt, Germany, where it was first created in 1994, has no practical uses due to its very short half-life and is only produced in particle accelerators. Expected to have properties similar to platinum based on its position in the periodic table. So, Roentgenium or G, named after Wilhelm Conrad Röntgen, discoverer of X-rays, first synthesized in 1994 by scientists at the GSI in Darmstadt, Germany. Its chemical properties are not well known due to its brief existence and rarity. So, copernicium, which is the last transition metal on the table. So, named after Nicolaus Copernicus, the astronomer who proposed the heliocentric model of the solar system, first created in 1996 by a team at the GSI in Darmstadt, predicted to be a metal possibly behaving like mercury, but is difficult to study due to its short half-life. It feels like I've said that so many times at this point. So, neodymium NH. Wait, no. Maybe there's two names for it. I don't know if there's two names for it because this has a symbol NH, atomic number 113, but on my this is the former, and this is an old table, so it says, can we see it? UUT, unatrinium, but it's the old name, so I think the new name is neodymium NH. Maybe it's an old periodic table, I'm not sure. Named after the Japanese word neon, meaning Japan, where it was first discovered. Synthesized in 2004 by the Riken Research Institute in Japan. Extremely radioactive with a short half-life and is mainly of interest for nuclear research. So, fluorovium FL. So, named after Laboratory of Nuclear Reactions in Dubna, Russia. First synthesized in 1998, is predicted to have properties similar to lead and tin. Studies indicate it may have unusual chemical properties compared to lighter group 14 elements. So, Moscovium MC. Wait, there may be a few that since have different names. My table at the end is different. So I think because they are newer elements, I'm just gonna go by on the computer because the table that I'm going seems to be wrong. So you're gonna see the wrong symbols here, but 115 is meant to be MC Moscovium, so named after Moscow, reflecting the collaboration between Russia and American researchers in its discovery. First created in 2003 at the Joint Institute for Nuclear Research in Dubna, highly unstable and studied mainly for its nuclear characteristics. Livermorium alpha, named after the Lawrence Livermore National Laboratory in California, which contributed to its discovery. First synthesized in 2000 by a collaboration between Russian and American scientists. Like other super heavy elements, it exists for only fractions of a second and used in research. So, Tennessine TS, named after the U.S. state of Tennessee, recognizing contributions from Oak Ridge National Laboratory, Vanderbilt University, and the University of Tennessee. First synthesized in 2010 by a collaborative team of the United States and Russia, predicted to exhibit properties similar to other halogens, but its extreme radioactivity and short half-life make directed studies difficult. Okay, so the last one on the table is Oganesson OG. and super heavy elements. First synthesized in 2002 by a team of the Joint Institute for Nuclear Research in Dubna, Russia, predicted to be a noble gas, but is expected to behave differently from other noble gases due to relativistic effects. Its properties are largely theoretical due to its short half-life of less than a millisecond. So yes, that is the whole periodic table that we did there. I hope you enjoyed. Thank you so much for watching this video. I tried to get straight to the point in this one more than the other one. Then again, like, even if I'm rambling a lot, I might have said I was rambling a lot, etc. But then I've, in editing, just decided to cut it out a lot of the time. So you never hear that. But either way, thank you so much for watching. I hope you enjoyed.